much. Thank you. Now our second presentation is prepared by Mr. Lazakis and Mr. Daya from the University of Strathclyde. I see Mr. Daya. Welcome to our Congress, sir.
Thank you. Good morning, all.
Good morning. Can you please kindly introduce yourself and then start your presentation? You have 15 minutes.
Yeah, all right. Thank you.
Ayhan hocam, tabii siz share screen'i kapatırsanız, you can take the share screen button, Mr. Daya, in the downwards in Zoom.
Yeah, that's what I'm trying to do, but it's not. It's saying that I cannot.
Okay, okay, now you can. I think our administrator helped you.
All right.
Thank you very much.
Yeah. Yes. Yeah, so my name is Abdullahi Daya. I'm from the University of Strathclyde. I'm studying PhD in marine engineering, and my main research area is on ship systems reliability. I'm currently serving with the Nigerian Navy as a marine engineer, and I'm of the rank of a commander. So this morning, I will be presenting on the application of artificial neural network and dynamic fault tree analysis to enhance reliability in predictive ship machinery health condition monitoring. To do this, I will be discussing introduction, motivation of the research, background and literature review, my methodology, machinery data analysis, results and discussions. Then we'll look at future work. Maintenance. The desire to achieve a reliable and uninterrupted power supply on board ship necessitated the need to have multiple power supply systems, either in parallel or individually, just to make sure that the ship is always available. This is also to ensure that there is reduction in risk to navigation, and also there is enhanced safety. Therefore, to improve this, there is need for an organized way to ensure that these machineries are always operational and available. Therefore, maintenance is defined as a combination of technical, administrative, and managerial actions during the life cycle of an equipment. However, overall maintenance takes a lot of cost in ship operations and operation costs. Also, we are aware that poorly maintained equipment increase overall cost of operation. And also in the naval balance, apart from the cost of operation, you also look at the challenge to national security. And again, if your systems are not maintained effectively, you also have the challenge to climate conditions, as a lot of things now to do with efficient operation of systems. Accordingly, my aim is to develop a hybrid maintenance framework using dynamic fault tree analysis and artificial neural network for predictive machinery health monitoring. That's the overall aim of the research. What motivated the research is the utilization of condition monitoring data for ship life cycle management. A lot of time you discover that ships towards the end of their life, there's a lot of challenge, and which I feel if there's proper record keeping, we may be able to have a better life towards the end of the ship. Also, the relevance of maintenance to reducing the environmental impact of shipping operations. Therefore, the objective of this study is to identify research gaps in maintenance concept and strategy in ship maintenance, to conduct reliability-based study on marine diesel generators and diesel engines, to also establish critical ship equipment failure pattern and use of machinery failure and parametric data for diagnostic and reliability studies. Within this period, we've conducted extensive literature review to show which aspect of maintenance is most reviewed and which is actually being used in the industry. So for instance, in the maritime industry, there is a lot of interest in condition-based maintenance, while overall in other industries, power generation, nuclear manufacture, offshore oil and gas, there is still interest in condition-based maintenance and PMS. I also want to mention that maintenance approach like RCM is still being used, but generally in the maritime industry is mainly to do with naval shipping. So over time, the advance in maintenance has led to emergence of a fifth generation of maintenance, which has been on the Internet of Things, or also referred to Industry 4.0. This is more or less due to the advancement in sensor technology, and also due to the pressure on the shipping industry to reduce its impacts due to greenhouse emission. So a lot of operators are shifting towards condition-based maintenance to mitigate emissions and also reduce high rate of consumption. The overall methodology for this study is hinged on three things: dynamic fault tree analysis, artificial neural network, and Bayesian belief network. The dynamic fault tree analysis is being used mainly for reliability analysis, criticality of equipment, and then artificial neural network is used for remaining useful life and classification of faults. Overall, this will come as inputs to an extent to the Bayesian belief network to help in maintenance strategy selection on board the ships or the entire fleet. To do this study, I have a case study ship, which is an OPV of the Nigerian Navy. She has a displacement of about 1,700 tons, about 95 meters in length. She's equipped with 2 diesel engines and 4 generators. Each of these generators can have a total output of 440 kVA. So for the ANN, we have the parameters, mainly the parameters of operational head for the generator, which were used between the operating ranges and the alarm. So this alarm is what I use to indicate faults. And when the operating range is close to the highest level, we look at it as a fault development. So this presentation is mainly to do with the DFTA, the reliability analysis. So the reliability analysis, I use the FTA, fault tree analysis, which is a procedure based on Boolean law by applying gates and events to describe faulty components and possible events that could develop to a fault. FTA is an important tool for reliability and risk analysis as it provides critical information used to prioritize the importance of contributors to the undesired event or fault. So, however, the challenge you have with the fault tree analysis, especially on board ships and how failure occurs, is that it is difficult to model sequence-dependent failures or temporal events. So that is why we decided to use the DFTA, which gives us this added advantage. So the DFTA added additional 4 gates to the traditional FTA. These 4 gates include the PAN gate, sequence enforcing gate, and functional dependency gate. Then we also have the spare gate, which models redundancy and also additional systems on the equipment or system to improve reliability. So what we are seeing here is a sample of the failure rate calculation. There are several methods you use in identifying unreliability in systems on the type of software I use, which include mean time to failure, frequency, failure rate, and time to repair. However, based on the data I have from the Nigerian Navy, I decided to use failure rate for components rather than the equipment itself. So we had to calculate individual failure rate based on aggregated failure rates. So what we are seeing here is the case study model of the 4 generators. On the upper part of the slide, you have the individual 4 generators that provided power for the power generation system. All the generators are connected in parallel, so you can have 2 generators operating at the same time. Then what you have in the lower part is actually the model of the individual systems. Overall, 9 systems were modeled. So these 9 systems include the crankcase, the moving parts, the fuel system, and most of the other systems that form of the diesel generator. So next, we are going to see the results we have. So on the far left is the power generation system reliability. I also need to add that the ship, based on the Nigerian Navy operational and maintenance period, is that each ship is supposed to have an availability of 80% over the period of the lifetime of the ship, usually 15%, 15 years before extended life refit. However, what we have on these generators is that within the first 12 months, we started noticing high level of unreliability. For instance, you can see on the power generation system, the level of reliability is very low. The power generation system entirely had a reliability of less than 80% within the first 12 months. So next is the combined reliability of the generators. This combined reliability of the generators shows the 4 generators and the power generation system. So here on the lower part, which you have the orange line, the DG1, you can see that it's much more unreliable even compared to the entire system. And in actual sense, at a certain point, the generator has to be pulled out of operation and be replaced with another one. So on the lower right, you have lower left, rather, you have the crankcase reliability, which is also the most unreliable component in the entire diesel generator system. So in most of the generators, you have the reliability of the crankcase falling at about the 40th month of the generator's operation. And these are generators that are expected to serve at least 12 years. And then in less than 3 years, they are almost going out of operation. The same thing when you come to the next component, you have the moving parts. We have very low reliability. And here again, if you look at the moving parts of the blue line, which is the DG1, if you compare it with the upper one, you could see that it's highly unreliable. So there was a lot of challenge in terms of that. And the next chart also shows the remaining other components, which is the air distribution system, the fuel system, the cooling system, and the inlet and exhaust system. Here we can see that the fuel system and the cooling system also show some level of high unreliability, and the inlet and exhaust of particular of DG3 was also unreliable. So now the next thing we did was to see what are the most unreliable components in the system and what are the most challenging failure types that require to be improved. So to do this, we have the reliability importance measures and the cut sets. These reliability importance measures are means to identify most critical component situation that contributes to the occurrence of the lowest basic event. So you have been bound, fissile vessel, and criticality. However, due to the size of the tree, I decided to use bin bound because it's much effective in kind of failure and modeling. While the cut sets is a combination of the minimum failures that can lead to the occurrence of the top event. So here, what we have here is the most critical components that contribute to at least 40% of failures in all the 4 generators. So in this, you could see in some areas, you could see heat exchanger tubes, for instance, in DG1. In DG2, there is still some problem, again, with heat exchanger tubes. In DG2, so in all of them, you could see there's some problem with heat exchangers, and in particular, cylinder head bolts. So this shows that there's problem with overheating and there's also problem with vibration. So these are like top 5 cut sets, which are the most prominent failures we have in all the 4 generators. So again, what you have here is the priority number in terms of importance in the generators. So what we have here, for instance, is that you can see that freshwater heat exchanger fouling appears in almost all the 4 generators. Then here again, you can see that tappet clearance appears again in almost all the 4 generators. So again, we could see that this is a very important problem that the operator needs to pay attention to. So next is, we try to see that, okay, after identifying these problems, failures, and critical components, how can we provide mitigating factors to see can it improve the reliability of the system. And we've been able to achieve that, for instance, for the DG1, which was a very reliable crankcase, with the use of the spare gates. So we tried to model, for instance, if the current engine seats were not helping to reduce the vibration on the engine, maybe we change the engine seat, and also try to introduce vibration monitoring on the generator. So by doing that, we have seen that the reliability of the generator from 22 months, it rose to about 34 months. So also on DG3 in the intake and exhaust system, it had problem with the valve clearance, and there was a lot of failures on the generator. We did that and we improved the availability with about 21 months. So these are some of possible advice we could give to operators in some areas where they can improve their maintenance actions or improve condition monitoring. So my future work is to look at sensitivity analysis in terms of the condition, and then to do diagnosis and degradation analysis. Also now use the overall output of Dfta and AAN for the BBN. So with this, I come to the end of this presentation, and thank you for listening, and I'm ready for any questions, please.
Thank you very much for your intriguing presentation, and you manage your time efficiently, Mr. Daya.
Yeah.
Are there any questions to Mr. Daya? I think we do not have any questions. Thank you very much.
Yeah.
Thank you very much.
Mr.
Thank you.